Imagine an equation so powerful that it describes almost every fluid in the universe. The air moving across an airplane wing, the swirling clouds inside a hurricane, the currents flowing through Earth's oceans, even the blood moving through your arteries. All of these systems follow the same mathematical rule. And yet, despite centuries of study, mathematicians still cannot answer one fundamental question about it. Does this equation always behave normally, or can it suddenly break and produce infinite chaos? If someone can prove the answer, they will receive $1 million. This is not a theory about aliens or dark matter. It is a real, unsolved problem in mathematics and physics. The equation is called the Navier-Stokes equations, and solving it is one of the famous Millennium Prize problems announced by the Clay Mathematics Institute. In fact, only one of the 7 Millennium problems has ever been solved so far, the Poincaré conjecture, solved by Russian mathematician Grigory Perelman in 2003. But the Navier-Stokes problem remains unsolved. And what makes it so strange is that scientists already use the equation every day. Aircraft designers use it, climate scientists use it, oceanographers use it. It predicts fluid motion incredibly well. But there is a catch. No one has been able to prove that the equation always produces smooth physical solutions. Some mathematicians suspect that under extreme conditions, the equations might produce something impossible, a mathematical singularity in a fluid, an explosion of infinite velocity, a breakdown of the mathematics itself. And that possibility opens one of the deepest mysteries in physics. To understand why this equation is so difficult, we first need to understand something more basic. What exactly is a fluid? In everyday life, we usually think of fluids as liquids like water or oil. But in physics, the definition is broader. A fluid is any substance that continuously deforms when a force is applied. This includes liquids like water, gases like air, plasma and stars, even large-scale flows of galaxies. If you push on a solid object, it resists the force, but if you push on a fluid, it flows. This simple behavior leads to some incredibly complex mathematics. For centuries, scientists tried to understand fluid motion. Early work began with Isaac Newton, who introduced the concept of viscosity, the internal friction inside a fluid. Viscosity determines how easily a fluid flows. Honey flows slowly because it has high viscosity. Water flows easily because it has low viscosity. Air has extremely low viscosity, which is why it moves freely around objects. But viscosity alone cannot explain all fluid behavior. In the 18th and 19th centuries, scientists realized that fluid motion depends on several factors at once: pressure differences, viscosity, external forces, and inertia of the fluid itself. Combining all these factors into one equation was incredibly difficult. Finally, 2 scientists independently developed the equations that describe fluid motion. French engineer Claude-Louis Navier first derived a mathematical model in 1822. Later, Irish mathematician George Gabriel Stokes refined the theory in 1845. Together, their work became known as the Navier-Stokes equations. These equations combine Newton's laws of motion with the physics of fluids. At their core lies the same fundamental principle that governs everything from falling apples to orbiting planets: Newton's second law. At the heart of fluid dynamics lies a very familiar physical law. This is Newton's laws of motion, developed by Isaac Newton in the 17th century. It states that force equals mass times acceleration. For a single object, this equation is simple. Push a ball and it accelerates. Pull a cart and it moves forward. But fluids are not single objects. A fluid contains trillions of tiny particles moving simultaneously. Each tiny portion of the fluid experiences forces from pressure differences, viscosity, gravity, surrounding fluid motion. Instead of tracking every molecule individually, physicists treat fluids as continuous fields. In this approach, every point in the fluid has properties like velocity, pressure, density. These properties change over space and time. When Newton's law is applied to every tiny element of the fluid, the result becomes the full Navier-Stokes equation. It describes how the velocity field of a fluid evolves over time. In simplified form, the equation looks like this. This single equation contains several physical effects: inertia of the moving fluid, pressure forces inside the fluid, viscous friction, and external forces such as gravity. In principle, solving this equation allows scientists to predict every possible fluid motion, from the smallest ripple in a pond to the largest storms in Earth's atmosphere. But there is a serious problem. When fluid motion becomes chaotic, the mathematics becomes almost impossible to solve. This chaotic regime is called turbulence, and turbulence is where the Navier-Stokes mystery truly begins. At first glance, fluids seem simple. Pour water into a glass and it flows smoothly. Watch smoke rise from a candle and it drifts gently upward. This kind of motion is called laminar flow, a smooth, orderly movement where fluid layers slide past each other. But under the right conditions, something dramatic happens. The smooth motion suddenly breaks. Swirls appear, eddies form. The flow becomes chaotic. This chaotic regime is known as turbulence. Turbulence is everywhere in nature. You see it in the swirling pattern behind a moving car, clouds inside storms, ocean currents colliding, smoke twisting in the air. Even the flow of interstellar gas in galaxies can become turbulent. Despite being so common, turbulence remains one of the most difficult problems in physics. In fact, the famous physicist Richard Feynman once said that turbulence might be the most important unsolved problem in classical physics. But why does turbulence appear at all? The answer lies in something called the Reynolds number. In the 19th century, physicists began to realize that fluid behavior depends on a delicate balance between two forces. One force tries to keep the flow smooth and orderly. The other tries to make the flow chaotic and unstable. These two forces are viscosity, internal friction in the fluid, and inertia, the tendency of the fluid to keep moving. To measure which effect dominates, scientists use a dimensionless quantity called the Reynolds number, named after physicist Osborne Reynolds. The Reynolds number is defined as Re equals rho v L over mu, where rho is fluid density, v is velocity, L is a characteristic length, and mu is viscosity. When the Reynolds number is small, viscosity dominates. The fluid moves in smooth layers. When the Reynolds number becomes large, inertia dominates, and that is when turbulence begins. For example, a slow-moving stream of honey has a very low Reynolds number, but air flowing around a jet airplane has a very high Reynolds number, and high Reynolds numbers create extremely complex flow patterns. Once turbulence begins, predicting the motion of the fluid becomes incredibly difficult. But the real mystery goes even deeper, because turbulence creates structures that seem almost alive. When turbulence appears, the fluid does not simply become random. Instead, it forms swirling structures called vortices. You can see vortices everywhere: water spiraling down a drain, tornadoes twisting through the atmosphere, whirlpools forming in rivers. Even galaxies can form vortex-like structures in interstellar gas clouds. These rotating structures can interact in complex ways. Vortices stretch, vortices split, vortices collide, vortices create smaller vortices. This leads to something physicists call an energy cascade. Large swirls break into smaller swirls. Those smaller swirls break into even smaller ones. Energy flows from large scales to tiny scales in a continuous chain. The Russian mathematician Andrei Kolmogorov developed one of the most famous theories describing this process. His theory suggested that turbulence follows a universal statistical pattern known as Kolmogorov turbulence. According to this theory, energy cascades down through many scales until it reaches a tiny size where viscosity finally dissipates it as heat. But here is the disturbing part. The Navier-Stokes equations allow this cascade to continue toward infinitely small scales. And if that happens, the velocity of the fluid might become infinite, a true mathematical singularity. This possibility is exactly why mathematicians still cannot prove whether the Navier-Stokes equations always behave properly. If such singularities exist, the equations would break down. And that brings us to the heart of the million-dollar mystery. When turbulence begins, energy in the fluid does not disappear. Instead, it travels through a fascinating process called the energy cascade. Imagine stirring a cup of coffee. At first, the spoon creates large swirling motions in the liquid. These large swirls are unstable. They quickly break into smaller vortices. Those smaller vortices break into even smaller ones. This process continues again and again. Large eddies transfer energy to smaller eddies, which then transfer energy to even smaller structures. Eventually, the energy reaches such tiny scales that the viscosity of the fluid finally dissipates it as heat. This idea was first described mathematically by Andrei Kolmogorov in 1941. Kolmogorov proposed that turbulence has a universal structure. According to his theory, the statistical behavior of turbulent flows becomes independent of the specific fluid once the Reynolds number is very high. In other words, turbulence in water, air, or plasma should follow the same universal mathematical patterns. Kolmogorov predicted a famous scaling law for turbulence energy. E of k is proportional to k to the power of -5/3. This relationship describes how energy is distributed across different scales in turbulent flow. Experiments in wind tunnels and atmospheric measurements have confirmed this prediction remarkably well. Yet, despite these successes, Kolmogorov's theory does not solve the deeper mathematical problem. Because it assumes that the Navier-Stokes equations remain smooth and well-behaved, and that assumption is exactly what mathematicians are trying to prove. To understand the real difficulty of the Navier-Stokes problem, we must think about something unusual, a mathematical explosion. In mathematics, certain equations can suddenly produce quantities that become infinitely large. These are called singularities. Singularities appear in many areas of physics. For example, the equations of general relativity developed by Albert Einstein predict singularities inside black holes. At the center of a black hole, density becomes infinite and space-time curvature diverges. But in general relativity, these singularities occur in extreme cosmic environments. In fluid dynamics, something far stranger might happen. The Navier-Stokes equations might produce singularities inside ordinary fluids. Imagine a region of fluid where velocity becomes infinite, vorticity becomes infinite, energy concentrates into an infinitely small point. If this occurs, the equations would mathematically break down. Physicists call this a blow-up solution. So the central question of the Navier-Stokes millennium problem is surprisingly simple to state. Do smooth solutions exist for all time, or can the equations produce singularities in finite time? Despite decades of research, no one has been able to answer this question. And the difficulty becomes even clearer when we look at how scientists actually try to solve these equations. You might think that modern computers could simply simulate the Navier-Stokes equations and check whether singularities appear. After all, today's supercomputers can perform quadrillions of calculations per second. But turbulence creates an enormous challenge. Remember the energy cascade? Large vortices break into smaller ones. Those smaller vortices break into even smaller structures. To simulate turbulence accurately, a computer must track every scale of motion, from large ocean currents spanning kilometers down to tiny viscous structures that may be millions of times smaller. This range of scales is called the turbulence spectrum. As the Reynolds number increases, the number of scales grows dramatically. For realistic flows, the required computational resolution becomes astronomically large. Even the most powerful computers cannot fully resolve all these scales. Instead, scientists use approximate methods, such as direct numerical simulation, DNS, large eddy simulation, LES, and Reynolds average Navier-Stokes models, RANS. These methods allow engineers to approximate turbulent flows, but they do not solve the mathematical question of whether singularities can exist. In other words, computers can simulate turbulence, but they still cannot prove that the Navier-Stokes equations always behave properly. And that is why the problem remains unsolved. To see how serious this challenge is, we need to look at the famous mathematical prize that made the Navier-Stokes mystery world famous. The difficulty of the Navier-Stokes problem became so important that in the year 2000, the Clay Mathematics Institute announced one of the most famous challenges in modern mathematics. They selected 7 of the deepest unsolved problems in mathematics and offered $1 million for each solution. These became known as the Millennium Prize problems. Among them were problems connected to number theory, topology, and mathematical physics. One of them was the Navier-Stokes existence and smoothness problem. The challenge is deceptively simple. Take the equations that describe fluid motion, assume that the fluid begins in a smooth and well-behaved state, then ask a fundamental question. Will the equations always produce solutions that remain smooth for all time? Or will something strange happen, a sudden mathematical breakdown where velocity or vorticity becomes infinite? If someone can prove that smooth solutions always exist, the equations are mathematically safe. But if someone proves that singularities can form, it would reveal something astonishing about the mathematics of fluids. What makes this puzzle especially fascinating is that physicists already use the Navier-Stokes equations successfully in countless real-world situations. Airplane aerodynamics, ocean circulation, weather prediction, and industrial fluid flows all rely on these equations. Yet the underlying mathematical guarantee does not exist. In other words, engineers are flying airplanes using equations that mathematicians have not fully proven to be stable. To understand why the proof is so difficult, mathematicians must translate the physical equations into precise mathematical language. At the core of the problem lies the equation that describes fluid motion. In this expression, the symbol v represents the velocity field of the fluid. Instead of tracking individual particles, the equation describes how the velocity changes at every point in space and time. The left side of the equation represents inertia, the tendency of fluid elements to keep moving. The right side represents forces such as pressure gradients, viscosity, and external influences like gravity. Although the equation may look compact, it hides enormous complexity. The term involving the velocity interacting with its own gradient introduces nonlinear behavior. Nonlinear equations are notoriously difficult because small changes in the system can produce dramatically different outcomes. This nonlinear interaction is precisely what allows turbulence to form. Mathematicians therefore ask a very precise question about the solutions of this equation. If we start with smooth initial conditions, will the velocity field remain smooth forever? Or can it suddenly develop infinite spikes in velocity or rotation? To analyze this question, mathematicians distinguish between different types of solutions. The most desirable case is called a smooth solution. In this situation, the velocity and pressure fields remain finite and differentiable at every point in space and time. Smooth solutions behave nicely. They can be analyzed, predicted, and understood using standard mathematical tools. But sometimes equations allow a weaker type of solution. These are known as weak solutions. Weak solutions may not be perfectly smooth. Instead, they satisfy the equations in an averaged or integrated sense. The French mathematician Jean Leray made an important breakthrough in 1934 by proving that weak solutions to the Navier-Stokes equations always exist. This was a major step forward. It showed that the equations do not simply collapse into nonsense. However, Leray's work did not answer the deeper question. Weak solutions might contain hidden singularities. They might allow regions where velocity becomes extremely irregular or even infinite. The Millennium Prize problem asks whether smooth solutions exist for all time or whether singularities inevitably appear. For decades, mathematicians have tried to attack this problem from many different directions. Some approaches attempt to prove that the energy of the fluid always remains bounded. Others try to analyze the structure of vortices and their interactions. Still others study simplified versions of the equations in lower dimensions. Interestingly, when the Navier-Stokes equations are restricted to 2 dimensions, mathematicians have already proven that smooth solutions always exist. But the real universe is 3-dimensional. In 3-dimensional turbulence, vortices can stretch and amplify each other. This phenomenon is known as vortex stretching. When a vortex tube stretches, its rotational speed increases, much like a spinning ice skater pulling in their arms to spin faster. Vortex stretching can transfer energy into smaller and smaller scales of motion.
If this process continues indefinitely, the mathematics might generate a singularity. That possibility is exactly what mathematicians are trying to rule out or prove. The difficulty of the problem has attracted some of the greatest mathematical minds of the past century. Among them was the Soviet mathematician Olga Ladozhenskaya, who made major advances in the theory of partial differential equations and fluid mechanics. Another influential figure was Vladimir Arnold, who explored the deep geometric structure of fluid motion. Arnold showed that fluid flows could be understood using ideas from geometry and topology, revealing unexpected connections between fluid dynamics and the mathematics of curved spaces. These discoveries hinted that the Navier-Stokes equations may hide deeper mathematical structures that scientists still do not fully understand. Even today, the problem remains one of the central challenges in mathematical physics. To appreciate how deep this mystery goes, we must step into an even stranger territory, the world of chaos theory, where tiny changes in fluid motion can lead to enormous differences in behavior. And once chaos enters the picture, predicting fluid motion becomes one of the hardest tasks in science. Fluid motion seems ordinary at first. Water flows, air moves, clouds drift across the sky. But beneath this simple appearance lies a system that can behave with extraordinary complexity. When scientists began studying turbulent flows carefully, they discovered that fluid motion often behaves like a chaotic system. Chaos does not mean pure randomness. In physics, chaos refers to systems that obey deterministic laws but are extremely sensitive to their initial conditions. A tiny difference in the starting state can grow into a completely different outcome. This idea became famous through the work of meteorologist Edward Lorenz in the 1960s. While studying atmospheric circulation, Lorenz discovered that extremely small rounding errors in his weather simulations caused the entire predicted weather pattern to change dramatically. This phenomenon became known as the butterfly effect. The name comes from the metaphor that a butterfly flapping its wings might eventually influence the formation of a distant storm. In turbulent fluids, similar sensitivity occurs constantly. Tiny variations in velocity or pressure can grow rapidly, producing entirely new flow patterns. This sensitivity makes turbulence extraordinarily difficult to predict. Even if scientists know the governing equations perfectly, the chaotic nature of the system means that long-term predictions become unreliable. The mathematical framework used to describe this sensitivity is known as chaos theory. Chaos theory revealed that many physical systems contain structures called strange attractors, which represent the long-term behavior of chaotic systems in phase space. Lorenz's weather model produced one of the most famous examples: the Lorenz attractor. The Lorenz attractor forms a beautiful butterfly-shaped structure when plotted in three-dimensional phase space. Even though the system is chaotic, its behavior remains confined within a specific region. This discovery showed that chaos has an underlying structure. Turbulence appears to behave in a similar way. Although turbulent flows look random, they contain hidden patterns and statistical regularities.
For example, turbulent flows tend to produce similar vortex structures across many different fluids. The swirling eddies in atmospheric storms resemble those found in laboratory water tanks. This universality suggests that turbulence may follow deep mathematical laws that scientists have not yet fully uncovered. However, chaos introduces a serious obstacle to solving the Navier-Stokes problem. Because chaotic systems amplify tiny disturbances, the velocity field of a turbulent fluid can become extremely irregular. The gradients of velocity, which measure how quickly the flow changes in space, can grow extremely large. If these gradients grow without bound, the equations could develop a singularity. This possibility connects turbulence to another important concept in nonlinear physics: energy concentration. In many nonlinear systems, energy can focus into smaller and smaller regions of space. Instead of spreading smoothly, the energy collapses into localized structures. This process occurs in phenomena such as shock waves, optical solitons, and plasma instabilities. Fluid turbulence may exhibit similar behavior. As vortices stretch and twist, they can concentrate vorticity into thin filament-like structures. These structures are sometimes called vortex tubes.
Inside a vortex tube, the rotational motion of the fluid becomes extremely intense. Measurements in turbulent flows show that vorticity can become thousands of times larger than the surrounding fluid. If vortex stretching continues indefinitely, it might drive the system toward a mathematical singularity. This is one of the main reasons the Navier-Stokes problem remains unsolved. Mathematicians must determine whether viscosity always prevents this runaway amplification. Viscosity acts like a smoothing force in the fluid. It dissipates energy and tends to suppress extreme gradients in velocity. In many cases, viscosity stabilizes the flow and prevents singularities from forming. But the competition between vortex stretching and viscous dissipation is delicate. If vortex stretching becomes stronger than dissipation, the equations might lose smoothness. Understanding this balance requires extremely sophisticated mathematical tools from the field of partial differential equations. Partial differential equations describe systems where physical quantities depend on multiple variables, such as space and time. The Navier-Stokes equations belong to this category. They describe how the velocity and pressure of a fluid evolve throughout a three-dimensional region. Analyzing such equations requires techniques from functional analysis, harmonic analysis, and geometric methods. Some mathematicians attempt to control the growth of velocity gradients by studying the energy of the system. If the total energy remains bounded, it may prevent singularities from forming. Others study the geometry of vortex structures, hoping to identify patterns that restrict the evolution of the flow. Despite decades of effort, a complete proof has remained elusive. The challenge is not merely technical. The Navier-Stokes equations sit at the intersection of several deep areas of mathematics and physics. They involve nonlinear dynamics, geometry, statistical physics, and even connections to quantum field theory. In fact, some physicists suspect that understanding turbulence may require entirely new mathematical ideas. One reason for this suspicion comes from the extraordinary complexity of turbulent flows. In high Reynolds number turbulence, the number of active degrees of freedom can become enormous. Each vortex interacts with many others across a wide range of scales. This creates a system with millions or even billions of interacting components. Such systems often exhibit emergent behavior, where large-scale structures arise from the collective interactions of many smaller elements. Emergence is common in complex systems throughout physics. Examples include the formation of galaxies in cosmology, collective behavior in plasma physics, pattern formation in chemical reactions.
Turbulence appears to be another example of this phenomenon. Some researchers believe that the key to solving the Navier-Stokes problem lies in understanding these emergent structures rather than focusing only on individual fluid elements. Others explore connections between turbulence and statistical mechanics. Statistical mechanics studies how large systems of particles produce macroscopic behavior, such as temperature and pressure. Similarly, turbulence may be governed by statistical laws that describe the distribution of energy across different scales. These ideas have led to the development of statistical turbulence theory, which attempts to describe turbulent flows using probability distributions rather than exact solutions. Although this approach has produced many useful insights, it still does not provide a rigorous proof of smoothness or singularity formation. The Navier-Stokes equations, therefore, remain one of the deepest mysteries in classical physics. They are simple enough to write on a single line of mathematics, yet they describe a phenomenon so complex that the greatest mathematicians in the world have struggled to fully understand it. And the deeper scientists explore turbulence, the more connections they discover with other fundamental areas of physics. Some researchers even believe that the mathematics of turbulence may reveal insights about cosmic phenomena, including the behavior of plasmas in stars and the dynamics of interstellar gas. The same equations that describe water flowing through a pipe may also describe the motion of matter across entire galaxies. This astonishing universality is one reason the Navier-Stokes equations continue to fascinate scientists. But the mystery becomes even deeper when we look at how turbulence appears in some of the most extreme environments in the universe. Environments where fluids interact with magnetic fields, relativistic speeds, and enormous cosmic scales. And in those extreme regimes, the physics becomes even more surprising. Fluid motion does not only exist on Earth. The same fundamental laws that describe water flowing in a river
also govern some of the most dramatic phenomena in the universe. In space, matter often behaves like a fluid. Giant clouds of gas drift through galaxies. Stars eject plasma into interstellar space, and enormous streams of charged particles flow around black holes. These systems are so large that individual particles become impossible to track. Instead, physicists describe them using the same principles of fluid dynamics. One of the most fascinating examples appears inside stars. The interior of a star is not a quiet place. Hot plasma rises, cool plasma sinks, and enormous convective currents move energy outward from the core. These flows are highly turbulent. The plasma inside the sun, for example, forms vast circulating cells thousands of kilometers across. These turbulent motions interact with the sun's magnetic field and help generate the solar magnetic cycle. This process is described by a branch of physics known as magnetohydrodynamics. Magnetohydrodynamics extends the Navier-Stokes equations by including electromagnetic forces. In such systems, charged particles move through magnetic fields, and the fluid motion itself can twist and stretch those fields. The result is a complex feedback loop. Fluid motion affects magnetic fields, and magnetic fields influence the motion of the fluid. This interaction creates some of the most powerful phenomena in astrophysics. Solar flares, for example, release enormous bursts of energy when magnetic fields in the sun's atmosphere suddenly rearrange themselves. Turbulent plasma motion plays a crucial role in triggering these events. Similar processes occur around neutron stars and black holes. When gas falls toward a black hole, it forms a rotating structure called an accretion disk. Inside this disk, matter moves at tremendous speeds, while turbulence transports angular momentum outward. Without turbulence, matter could not spiral inward efficiently, and black holes would grow far more slowly. The equations describing these cosmic flows are closely related to the Navier-Stokes equations, although additional physics such as relativity and electromagnetic forces must be included. This reveals something remarkable about the equations of fluid motion. They apply across an enormous range of scales. The same mathematics can describe the swirling milk in a cup of coffee and the turbulent plasma surrounding a black hole millions of times more massive than the sun. Few equations in physics have such universal reach. Yet the mathematical foundations of these equations remain incomplete. The Navier-Stokes equations belong to a class of mathematical expressions known as nonlinear partial differential equations. Nonlinearity means that different parts of the system interact with each other in complicated ways. In linear systems, small causes produce small effects. But in nonlinear systems, tiny disturbances can grow rapidly and produce entirely new structures. This is why turbulence is so unpredictable. A small disturbance in a fluid can grow into a vortex, which then interacts with other vortices, producing cascades of motion across many different scales. Mathematically, the difficulty arises from the nonlinear term that represents the interaction of the velocity field with itself. This term describes how the fluid motion transports and distorts its own velocity field. In simple language, the fluid is constantly reshaping its own flow pattern. Because of this self-interaction, solutions of the Navier-Stokes equations can become extremely complicated. The equations are deterministic, meaning that their future behavior is completely determined by the initial conditions. Yet the nonlinear interactions make long-term prediction extremely difficult. To understand how complicated turbulent motion can become, imagine the atmosphere of Earth. The atmosphere is essentially a giant fluid layer surrounding the planet. Its motion is governed by fluid dynamics combined with thermodynamics and planetary rotation. Warm air rises, cold air sinks, pressure differences drive winds, and the rotation of Earth introduces the Coriolis effect. Together, these processes create storms, jet streams, and large-scale circulation patterns. Even with modern satellites and powerful supercomputers, predicting the weather beyond a few weeks becomes extremely challenging. This is partly because atmospheric motion is turbulent. Tiny uncertainties in the initial state of the atmosphere grow rapidly through chaotic interactions. As a result, long-term predictions become unreliable. This limitation illustrates the deep connection between turbulence and chaos. But the Navier-Stokes mystery goes beyond prediction. The Millennium Prize problem asks a much more fundamental question: whether the equations themselves can break down. If singularities exist, they would represent points where the mathematical description of the fluid ceases to work. Velocity gradients might become infinitely steep, creating structures that no physical fluid could sustain. Some researchers suspect that if such singularities occur, they would appear as extremely thin vortex filaments where energy concentrates intensely. Others believe that viscosity always smooths out the flow before a singularity can form. Despite decades of work, neither possibility has been proven. Mathematicians have developed many partial results. They have shown that singularities cannot occur under certain special conditions. They have also demonstrated that smooth solutions exist for short periods of time. But a general proof for all three-dimensional flows remains beyond reach. This difficulty highlights an important truth about physics. Even equations that appear simple can contain hidden depths. The Navier-Stokes equations consist of only a few mathematical terms, yet they encode an enormous range of physical behaviors, from gentle laminar flow to violent turbulence, from laboratory experiments to cosmic plasma storms. Because of this richness, some scientists consider turbulence to be one of the last great unsolved problems of classical physics. Solving the Navier-Stokes problem would not only answer a mathematical question, it would also deepen our understanding of fluid motion across nature and technology. It might improve weather prediction, climate modeling, aircraft design, and the study of astrophysical plasmas. But more importantly, it would reveal something profound about how complexity arises from simple physical laws. And that raises a deeper question. If such complexity can arise from a single equation describing fluids, what other hidden mysteries might still be waiting inside the fundamental equations of physics?
To see how deep the Navier-Stokes mystery goes, mathematicians examine the structure of the equations with extreme precision. These equations belong to a powerful class of mathematical objects known as partial differential equations, which describe how physical quantities change across space and time. Unlike ordinary equations that involve a single variable, partial differential equations involve functions that depend on many variables simultaneously. In the case of fluid dynamics, the velocity of a fluid depends on three spatial dimensions and time. At every point in space, the fluid has a velocity vector describing both its speed and direction. The Navier-Stokes equations describe how this velocity field evolves under the influence of pressure forces, viscosity, and external forces. The full structure of the equation can be expressed as: each term in this equation represents a specific physical process. The first term describes how the velocity changes over time. The second term represents advection, the process by which the motion of the fluid carries its own velocity patterns along with it. The pressure gradient term represents forces arising from differences in pressure within the fluid. The viscosity term accounts for internal friction, which smooths out sharp velocity differences. Finally, external forces such as gravity or electromagnetic effects can influence the motion of the fluid. The mathematical challenge lies in understanding how these terms interact in three-dimensional space. One particularly important feature is that the nonlinear advection term couples different regions of the fluid together. Motion in one region can influence distant regions through the propagation of vortices and waves. Because of this coupling, small disturbances can evolve into complex structures spanning many different scales. Mathematicians therefore study how energy moves within the fluid. The total kinetic energy of a fluid flow can be written as an integral over the entire domain.
Under certain conditions, this energy remains bounded for all time and decreases gradually due to viscous dissipation. If the energy remains bounded for all time, it may prevent singularities from forming. However, energy can also concentrate locally. In turbulent flows, energy moves from large-scale motion into increasingly smaller structures through the cascade process. This transfer across scales makes it extremely difficult to prove that no region will ever develop infinitely large velocity gradients. To investigate these possibilities, researchers analyze quantities such as vorticity, which measures the local rotation of the fluid.
Physicists understand the basic laws governing fluid motion, yet the consequences of those laws remain only partially understood. Interestingly, similar mathematical structures appear in other areas of physics. In plasma physics, nonlinear equations describe the behavior of charged particle fluids interacting with electromagnetic fields. In condensed matter physics, nonlinear field equations describe wave propagation in complex materials. Even in high-energy physics, the equations governing quantum fields exhibit nonlinear interactions reminiscent of those found in turbulence. These connections suggest that solving the Navier-Stokes problem might illuminate broader principles governing complex systems throughout physics. Some researchers believe that turbulence represents a fundamental form of self-organization, where order and structure emerge spontaneously from chaotic motion. Understanding this process may require new mathematical ideas that extend beyond traditional analysis. In recent years, scientists have also begun exploring turbulence using data-driven methods. Advanced simulations produce vast amounts of information about fluid flows, which can be analyzed using machine learning and statistical techniques. Although these methods have improved practical predictions, they have not yet resolved the core mathematical question. The Navier-Stokes equations continue to stand at the boundary between known physics and unexplored mathematical territory. They describe a universe of swirling motion, hidden structures, and chaotic interactions that still challenge the limits of human understanding. And somewhere within those equations lies the answer to a question that mathematicians have pursued for more than a century. Can the motion of a fluid remain smooth forever, or does nature allow the mathematics itself to tear apart under extreme conditions? To push further into the mathematics of fluid motion, scientists examine how the velocity field behaves in extremely small regions of space. Instead of looking at the entire fluid at once, they zoom in on tiny volumes and study how the motion evolves locally. At these small scales, the important quantity is vorticity, the measure of how strongly the fluid rotates around a point. Vorticity describes the microscopic spinning motion embedded within a larger flow. If you stir a cup of coffee and look closely, you will see tiny spinning patterns forming inside the liquid. Each of these small rotations corresponds to regions of strong vorticity. Mathematically, vorticity is defined as the curl of the velocity field. Here, the vector omega represents the local rotation of the fluid. Where vorticity is large, the fluid spins rapidly. Where vorticity is small, the flow is relatively smooth. The evolution of vorticity reveals much about turbulence. In two-dimensional fluids, vortices behave in a surprisingly stable way. They can move, merge, or interact, but they tend to preserve their overall structure. Energy in two-dimensional turbulence often flows toward larger scales, creating giant coherent vortices. In three-dimensional fluids, the situation changes dramatically. Vortices can stretch along their length. When this happens, the rotation becomes stronger. The stretching process amplifies vorticity and transfers energy into smaller scales of motion. This phenomenon is known as vortex stretching, and it is one of the defining features of three-dimensional turbulence. As vortex tubes stretch, they become thinner and more intense. In highly turbulent flows, researchers observe networks of extremely thin filaments where vorticity becomes concentrated. These structures represent locations where velocity gradients become extremely large. In mathematical terms, these regions are the most likely candidates for the formation of singularities. If the stretching process continues indefinitely, the vorticity could grow without bound. Viscosity, however, acts as a stabilizing force. As vortex tubes become thinner, viscous effects grow stronger and begin to diffuse the rotation. This competition between stretching and diffusion lies at the heart of the Navier-Stokes mystery. One side of the equation tries to amplify motion, while the other tries to smooth it out. Whether amplification can ever overwhelm diffusion completely remains unknown. To analyze this balance, mathematicians investigate quantities known as norms of the velocity field. Norms measure the overall magnitude of certain properties of the flow across the entire fluid domain. For example, the kinetic energy of the flow can be expressed as an integral of the velocity squared. If this quantity remains finite for all time, it provides partial evidence that the flow may remain well-behaved. Researchers derive inequalities that constrain how quickly these norms can grow. Such inequalities act like mathematical safety barriers that prevent certain kinds of singular behavior. However, proving that these barriers hold for all possible flows has proven extremely difficult. The challenge arises from the immense number of ways in which vortices can interact. In turbulent motion, thousands of vortices stretch, twist, collide, and reconnect simultaneously. Each interaction transfers energy between different scales of motion. These interactions produce the rich complexity observed in real fluid flows. Laboratory experiments reveal that turbulence often organizes itself into patterns that appear almost fractal in nature. Large vortices contain smaller vortices, which themselves contain even smaller structures. This hierarchy of swirling motion extends across many orders of magnitude. Fractal-like structures appear in many nonlinear systems throughout physics, including plasma turbulence, cloud formation, and galaxy clustering. The appearance of similar patterns across such different systems suggests that turbulence may follow deep universal laws. One way to investigate these patterns is through spectral analysis. Instead of describing fluid motion directly in physical space, scientists decompose the velocity field into waves of different wavelengths. Each wave represents motion at a particular spatial scale. The distribution of energy among these waves forms what physicists call the energy spectrum of turbulence. Experiments and simulations show that turbulent energy tends to follow specific scaling laws across intermediate ranges of wavelengths. These scaling relationships reveal how energy flows through the cascade process, from large structures to smaller ones. Yet, even these powerful statistical descriptions do not solve the core mathematical question. They describe average behavior rather than guaranteeing smooth solutions everywhere. A singularity could still appear in a tiny region of space, even if the overall statistical behavior of the fluid remains well-behaved. Because of this possibility, the Navier-Stokes equations continue to challenge mathematicians and physicists alike. The difficulty of the problem has led some researchers to explore entirely new perspectives. One idea is that turbulence might be related to geometric structures hidden within the equations themselves. Instead of viewing the equations purely as analytic objects, mathematicians study the geometry of the space of all possible fluid motions. In this viewpoint, fluid flows can be interpreted as trajectories moving through an abstract geometric landscape. The shape of this landscape determines how flows evolve and whether they can develop singular behavior. This geometric perspective was explored by mathematicians such as Vladimir Arnold, who showed that the motion of ideal fluids can be interpreted as geodesics on a curved, infinite-dimensional space. Arnold's work revealed unexpected connections between fluid dynamics and differential geometry. These connections suggest that the Navier-Stokes problem may ultimately require insights from several branches of mathematics working together. While researchers continue searching for a rigorous proof, the equations themselves remain one of the most powerful tools in science. They govern the movement of oceans, the dynamics of the atmosphere, the behavior of plasmas and stars, and the swirling gas clouds that shape galaxies. Every time the wind blows, every time waves crash against a shore, and every time smoke curls upward into the air, the Navier-Stokes equations are silently at work. Yet, hidden within those equations may be a phenomenon that no one has ever fully understood. A moment when a smooth motion of a fluid suddenly collapses into infinite complexity. And proving whether that moment can ever occur remains one of the greatest unsolved challenges in modern science.
As scientists continued investigating turbulent flows, they began to realize that turbulence is not simply disorder. Hidden beneath the chaotic motion lies a surprising level of organization. Even though turbulent flows look random to the human eye, careful measurements reveal statistical patterns that appear again and again in completely different systems. These patterns appear in laboratory water tanks, in atmospheric winds, in ocean currents, and even in the plasma surrounding distant stars. The fact that the same mathematical behavior appears across such different environments suggests that turbulence obeys universal physical principles. Researchers studying turbulence often describe it as a statistical state of motion rather than a perfectly predictable one. Instead of trying to follow every tiny eddy in a fluid, scientists analyze average properties such as energy distribution, vortex density, and probability distributions of velocity fluctuations. One of the remarkable discoveries in turbulence research is that the distribution of energy across different spatial scales follows surprisingly regular laws. Large structures contain most of the energy, while smaller structures carry progressively less. Yet the transfer of energy between these scales occurs continuously through the cascade process. This transfer forms a dynamic equilibrium, where energy injected at large scales moves steadily towards smaller scales until viscosity eventually dissipates it as heat. Such processes illustrate a deeper principle in physics. Complex structures can emerge from relatively simple equations. The Navier-Stokes equations themselves are not especially long or complicated. In fact, the fundamental mathematical expression describing fluid motion can fit on a single line. Yet from this compact formula emerges the astonishing diversity of fluid behavior observed in nature. Gentle streams flowing through valleys, powerful hurricanes forming over warm oceans, swirling patterns inside galaxies, and turbulent plasma inside stars can all be described by variations of the same mathematical structure. This universality is part of what makes the Navier-Stokes equations so fascinating. Few physical laws govern phenomena across such an enormous range of scales. At the same time, the equations also remind us that nature can be far more complex than the formulas used to describe it. The mathematical challenge of proving whether smooth solutions always exist has resisted every attempt so far. Some of the most brilliant mathematicians of the 20th and 21st centuries have explored the problem from different angles. Some search for hidden constraints that limit how quickly velocity gradients can grow. Others examine special cases of the equations where partial results can be obtained. Still others analyze simplified models that capture essential aspects of turbulence without including the full complexity of the original equations. Despite these efforts, the final answer remains unknown. Either the equations always remain smooth, meaning that turbulence never produces true mathematical singularities, or somewhere within the enormous landscape of possible flows, there exists a configuration where the mathematics breaks down. Both possibilities would reveal something profound. If smooth solutions always exist, it would confirm that physical processes of viscosity and diffusion ultimately stabilize fluid motion no matter how turbulent the flow becomes. But if singularities can occur, it would mean that even classical physics contains situations where its own equations lose predictive power.
Such a discovery would reshape our understanding of nonlinear systems and might influence other areas of physics where similar equations appear. The search for this answer continues in universities and research institutes around the world. Mathematicians explore new analytical techniques. Physicists perform high-precision experiments in wind tunnels and fluid laboratories. Supercomputers simulate increasingly detailed turbulent flows, generating enormous data sets that reveal previously unseen structures within the motion. Each of these efforts contributes pieces to a puzzle that has fascinated scientists for more than a century. And yet, the core mystery remains untouched. Somewhere within the elegant mathematics of fluid motion lies a question still waiting to be answered. Can the swirling motion of a fluid remain perfectly smooth forever? Or can the equations themselves collapse into infinite complexity? Until someone finds the proof, the Navier-Stokes equations will continue to stand as one of the deepest unsolved challenges in science. They remind us that even in a world governed by precise physical laws, nature still holds mysteries that push the limits of human understanding. And perhaps that is what makes science so powerful. Every equation we write is not just a description of the universe, It is also an invitation to explore the unknown.